Hello there, and welcome to the Sleep Science is Playing channel tonight, the quiet and almost entirely overlooked truth about emotion that has been carrying you, this planet, every ocean and mountain and sleeping city through the galaxy for longer than the Earth itself has existed. The sun is moving, not spinning in place, not simply holding the planets in their orbits, moving, drifting through the Milky Way at a speed so large it becomes meaningless without the right kind of patience to sit with it. And the direction it is heading, the direction directly in front of the solar system as it travels, is a patch of sky that almost no one has ever thought to look at deliberately. Over the next 2 hours, we will follow that motion. We will walk through what drives it, what lies ahead in the sun's path, what has already been passed, and what the long future of this drift means for the world you are sleeping on tonight. If these quiet explorations are worth your time, a like or a subscribe helps the channel reach others who need them. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in, let your shoulders drop, let your breathing find its own slow pace, let the day behind you grow distant and soft. Let's begin. There is a motion happening right now that is so large and so constant that the human mind has almost no instinct for registering it. You are aware, perhaps, that the Earth spins. One rotation every 24 hours, carrying you from daylight into darkness and back again. You are aware, perhaps, that the Earth orbits the sun, one long loop every year, carrying the planet through its seasons. These two motions are taught early and remembered easily because their effects are visible. The spinning produces the sunrise, the orbit produces the summer. The consequences are felt and the motions become real. But there is a third motion that is never taught with the same directness, and whose consequences are so slow and so vast that no human life is long enough. The direction the sun is currently heading has a name and a location in the sky. It is called the solar apex. The word apex simply means the forward point, the direction of motion, the place the traveler is heading toward. The solar apex is the point on the celestial sphere toward which the sun is moving when its motion is measured relative to the average motion of the nearby stars in our galactic neighborhood. The solar apex sits in the constellation of Hercules, specifically near a star in Hercules called Vega's neighbor, close to the boundary between Hercules and the constellation Lyra. The coordinates are well established, and the direction has been known to astronomers since the 18th century, when the British astronomer William Herschel first worked out that the sun must be moving by noticing that nearby stars seemed to be slowly drifting apart in one direction of the sky and slowly converging in the opposite direction. Stars ahead of the sun's motion appear to slowly spread outward as the sun approaches them. Stars behind the sun's motion appear to slowly draw together as the sun moves away from them. The effect is the same effect that makes the trees beside a road appear to spread apart as a car drives toward them. It is the geometry of motion projected against a distant background. Herschel's deduction was one of the quieter revolutions in the history of astronomy. The idea that the sun was itself in motion, that it was not the fixed center of everything, but rather a traveler moving through a larger system, was not an obvious one in the 18th century. The sun had been treated as a fixed point of reference for so long that the discovery of its own motion required a particular kind of careful observation and a willingness to let the data suggest something the observer had not been looking for. The solar apex is not a fixed point in an absolute sense. It depends on what the sun's motion is being measured relative to. Measured relative to the nearby stars in the immediate stellar neighborhood, sits in Hercules as described. Measured relative to the center of the Milky Way galaxy itself, the direction of motion is different, shifted into the constellation of Cygnus. The two measurements are not contradictory. They simply describe different aspects of the same motion. The local apex describes where the sun is heading relative to its immediate neighbors. The galactic apex describes where the sun is heading relative to the grand center of everything in the galaxy. For tonight, the direction that matters most is the local one, the apex in Hercules, because it is the direction into which the sun is physically traveling through the local interstellar neighborhood. It is the direction from which new interstellar material is approaching the heliosphere. It is the direction into which the bow of our bubble pushes as the sun moves through the surrounding gas. It is, in the most literal sense, the direction of the future, the direction toward which every moment is carrying us without pause or interruption. The sun does not travel through empty space. The region of the galaxy between the stars is not a perfect vacuum. It is filled with a thin, diffuse mixture of gas and dust, collectively called the interstellar medium. The interstellar medium is not uniform. It has regions of higher density and regions of lower density. It has warm regions and cool regions. It has regions threaded with magnetic fields and regions where the field is weaker or more tangled. It has enormous clouds of cold, dense gas where new stars are slowly forming, and vast hot cavities carved by the explosions of stars that have already died. The sun is currently passing through a particular small region of the interstellar medium called the local interstellar cloud. The local interstellar cloud is a warm, relatively low-density region of interstellar gas, mostly hydrogen and helium, that the sun entered somewhere between 45,000 and 150,000 years ago. The uncertainty in that number is large because the boundaries of the cloud are not sharp, and the sun's passage through them is gradual rather than abrupt. The cloud is not large by interstellar standards. It is roughly 30 light-years across, which sounds enormous but is quite modest in the context of a galaxy that is 100,000 light-years wide. The sun will exit the local interstellar cloud within the next few thousand to tens of thousands of years, depending on exactly where the cloud's boundary lies and exactly how the sun is moving relative to it. In cosmic terms, the exit is imminent. In human terms, it is so far in the future that no specific date is worth attaching to it. The sun is near the edge of the cloud it currently inhabits, and the edge is approaching at the speed of the solar system's drift through the local neighborhood. What lies beyond the local interstellar cloud in the direction of the solar apex, in the direction the sun is heading, is a region called the local bubble. The local bubble is a much larger cavity in the interstellar medium, roughly 1,000 light-years across, filled with extremely hot and extremely low-density gas. The local bubble is thought to have been carved by a series of supernova explosions over the past 10 to 20 million years. Massive stars in the local region of the galaxy reached the ends of their lives and exploded, blasting enormous quantities of hot gas outward and sweeping up the surrounding interstellar medium into a thin shell around the expanding cavity. The result is the large, relatively empty region that currently surrounds the sun and its immediate stellar neighbors. The local interstellar cloud in which the sun currently sits is itself embedded within the local bubble. The cloud is a small condensation within the larger cavity, a slightly denser knot of gas within a generally empty space. The sun is passing through this small cloud and will eventually emerge into the hotter, emptier interior of the local bubble before potentially encountering denser material scale at the bubble's far wall. Sit for a moment with what this means at the scale of the solar system itself. The heliosphere, the great bubble of solar wind that surrounds the sun and all its planets, is not a fixed structure. It breathes with the solar cycle, expanding and contracting as the sun's activity rises and falls, but it also responds to the external environment it is pushing through. The pressure of the surrounding interstellar gas pushes inward on the heliosphere from outside. The pressure of the solar wind pushes outward from inside. The boundary between them sits where these two pressures balance. When the external pressure is higher because the surrounding interstellar gas is denser or moving faster relative to the sun, the heliosphere is compressed. The boundary draws closer to the sun. The protective bubble that shields the inner solar system from the harsher conditions of interstellar space becomes smaller and tighter when the external pressure is lower because the surrounding gas is more diffuse or the sun's wind is stronger. The heliosphere expands outward and the boundary retreats to greater distances. The transition from the local interstellar cloud into the hotter, emptier interior of the local bubble would be a transition from a higher pressure external environment to a lower pressure one. The immediate consequence for the heliosphere would be expansion. The boundary would push outward. The bubble containing us would grow larger. The cosmic ray environment inside the heliosphere would change because cosmic rays from outside, which are partially deflected by the heliospheric magnetic field, would experience a differently shaped and differently sized barrier. These changes would unfold over tens of thousands of years, far too slowly for any individual lifetime or any civilization to observe in real time. They are the kind of changes that are reconstructed from evidence left in geological and biological records rather than observed directly. There is evidence in Antarctic ice cores and deep sea sediments of past changes in the cosmic ray flux reaching Earth's surface, changes that may reflect past changes in the heliosphere's size and shape as the sun passed through different regions of the interstellar medium. The record is indirect and difficult to read with precision, but the basic principle is well established. The environment through which the sun travels shapes the environment in which the Earth lives. The motion of the solar apex is not an abstract astronomical fact. It is a slow environmental variable whose changes, accumulated over millions of years, have contributed to the conditions on the surface of this planet across its long history. Behind the sun, in the direction opposite the solar apex, is a point called the solar antipex. It sits in the constellation of Columba, a small constellation in the southern sky below Orion. The antipex is the direction from which the sun has come, the direction of the past, the direction of the interstellar environments the solar system has already passed through and left behind.
The history encoded in the antipex direction is long and varied. Over the 4.5 billion years of the solar system's existence, the sun has traveled through many different regions of the Milky Way, passing in and out of spiral arms, drifting through regions of varying stellar density, encountering interstellar clouds of different compositions and densities. Each of these passages has left its mark, not on the sun itself, which is too massive and too energetic to be significantly altered by passing through interstellar gas, but on the outer reaches of the solar system, on the composition and distribution of comets, on the flux of cosmic rays that has reached the inner planets across deep time, and possibly on the history of life on Earth. The spiral arms of the Milky Way are regions of elevated stellar density, where star formation is more active and where massive short-lived stars are more common. A massive star lives for only a few million years before exploding as a supernova. Supernovae produce enormous fluxes of high-energy radiation and fast-moving particles, energetic enough to ionize planetary atmospheres and potentially to affect life on the surfaces of nearby worlds. As the Sun passes through a spiral arm, the probability of a nearby supernova increases significantly. The passages through spiral arms are thought by some researchers to be correlated with periods of increased extinction rates in Earth's fossil record, though the correlation is imprecise and the subject remains an area of active discussion rather than settled science. The Sun is currently between spiral arms in a relatively quiet interarm region. This is thought to be part of why the last several tens of millions of years have been a relatively stable period for life on Earth compared to some earlier chapters of geological history. The neighborhood is calm, the massive stars are mostly far away. The supernova rate in the immediate vicinity is low. The heliosphere presses against a relatively benign interstellar environment. None of this is permanent. The Sun's orbit will eventually carry it back into a spiral arm, and the neighborhood will become busier. But that transition is tens of millions of years away and is not something the night requires any attention to be paid toward. There is something deeply unusual about the direction the Sun is traveling when it is considered carefully. The solar apex in Hercules is a direction that points more or less upward out of the galactic plane at a slight angle. The Sun's motion through the galaxy is not perfectly circular and flat. It has a small component that carries it gently above and below the flat disk of the Milky Way as it orbits. The Sun oscillates up and down through the galactic plane with a period of roughly 60 to 70 million years, rising above the plane, reaching a maximum height of perhaps a few hundred light-years, then falling back through, descending below the plane, reaching a similar depth below and returning. A slow, gentle vertical oscillation superimposed on the long horizontal circuit around the galactic center. The Sun is currently moving upward, away from the galactic midplane, having crossed through the midplane relatively recently in astronomical terms, within the last few million years. The direction of this upward drift is tilted somewhat toward the solar apex. The Sun is heading forward and slightly upward at the same time, like a ship moving through the ocean on a heading that takes it both forward and gradually into slightly shallower water. The galactic plane itself is not uniform. The midplane of the Milky Way is where the density of gas and dust and young stars is highest. It is the most active region of the disk, where star formation is ongoing and where the interstellar medium is richest. As the Sun drifts above the midplane on its slow vertical oscillation, it moves into slightly less dense territory. Above the midplane, the density of the interstellar medium decreases. The sky in the perpendicular direction becomes slightly cleaner. The cosmic ray environment changes subtly. The Sun's neighborhood becomes a little quieter, a little emptier, a little more removed from the busiest traffic of the galactic disk. When the Sun eventually falls back through the midplane and descends below it, it passes through the densest regions again. Some researchers have suggested that these crossings of the galactic midplane might be correlated with periodic disturbances to the outer comet cloud that surrounds the solar system, the Oort cloud, and with periods of elevated comet flux into the inner solar system. The gravitational tides of the galactic disk, strongest near the midplane, might perturb the distant comets in their slow orbits and send some of them falling inward toward the Sun and planets. The evidence for this periodic comet shower hypothesis is suggestive but not conclusive. The timescales are long enough and the records incomplete enough that certainty remains elusive. But the principle is sound. The Sun's vertical position in the galaxy affects the gravitational environment of its outermost cometary population. The motion of the solar apex carries consequences that reach all the way out to the frozen objects drifting at the very edge of the solar system. Return now to the simpler and more immediate picture, the direction in Hercules toward which the Sun is traveling, the local stars in that direction, the interstellar medium in that region of the sky, the immediate future of the Sun's path as measured not over billions of years, but over the next few tens of thousands of years. Relative to the nearest stars, The sun's motion carries it at roughly 20 kilometers per second toward the solar apex. This is the local component of the motion, the speed relative to the immediate stellar neighborhood rather than relative to the galactic center. At 20 kilometers per second, the sun covers a light year every 15,000 years or so. The nearest star to the sun, the Proxima Centauri system, is slightly more than 4 light-years away. In roughly 60,000 years, the sun will have moved the equivalent distance of that nearest neighbor, though of course the nearest neighbor is itself moving and the relative geometry shifts continuously. The stars in the direction of the solar apex, the stars in Hercules toward which the sun is heading, appear to slowly spread apart as the sun approaches. This is the parallax of motion, the same spreading effect that Herschel noticed in the 18th century and used to deduce that the sun was moving. The stars in the direction of the antipodes, behind the sun, appear to slowly draw together as the sun moves away. The pattern is subtle and measurable only over timescales of thousands of years for the nearest stars, but it is real and it is happening continuously. No star lies directly in the sun's path. The gaps between stars are so enormous that even in the sun's long history of galactic travel, a direct collision with another star has never occurred and is extraordinarily unlikely in the sun's remaining future. The nearest approach of another star to the solar system in the foreseeable astronomical future will carry that star no closer than perhaps a light year or so, which in stellar terms is a comfortable miss. The stars of the Milky Way are not packed tightly enough for the sun's motion to bring it into close contact with any of them on any timescale that requires concern. What does lie in the sun's path is interstellar gas. The thin, diffuse material of the interstellar medium is distributed throughout the galaxy in structures of varying density, and the sun's motion carries it through these structures continuously. The local interstellar cloud currently surrounding the system is only the most recent in a long series of interstellar environments through which the sun has passed. Each one has slightly shaped the heliosphere, and through the heliosphere the conditions experienced by the inner planets. The next environment the sun will enter, the hotter, emptier interior of the local bubble, will in its turn shape the heliosphere differently, expanding it, altering the cosmic ray environment, changing in subtle ways the particle and field conditions experienced by the Earth and the other planets. There is a beautiful and rarely discussed consequence of the sun's motion through the local interstellar medium that takes a few unhurried sentences to appreciate properly. As the solar wind flows outward from the sun in all directions, it pushes against the surrounding interstellar gas and carves the heliosphere. But because the sun is moving through that gas, the interaction is not symmetric. On the side of the heliosphere facing the direction of travel, the upwind side toward the solar apex, the ram pressure of the sun's motion through the interstellar gas compresses the boundary inward. The interstellar gas piles up slightly on the forward side. On the opposite side, the downwind side toward the antipodes, the boundary is stretched outward into whatever shape the combined pressures of the solar wind and the wake of the sun's passage produce. The result, as described in the previous evening's exploration, is a heliosphere that is not a perfect sphere. It has a more compressed nose on the upwind side and a more extended structure on the downwind side. Whether that downwind extension is a long comet tail or a more compact, deflated shape is one of the open questions in heliospheric physics. But the asymmetry itself is a direct consequence of the sun's motion through the surrounding gas. The solar apex is not only the direction of astronomical interest, it is the direction from which the external pressure on our bubble comes. It is the direction that determines which side of the heliosphere is the compressed nose and which side is the extended wake. 2 spacecraft launched from Earth in the 1970s and now traveling far beyond the planets have both exited the heliosphere in directions that are roughly on the upwind side of the bubble, closer to the solar apex side than to the antipodes side. Their measurements of the boundary have therefore sampled the compressed nose region rather than the extended tail region. They have told us a great deal about how the heliosphere meets the interstellar medium on the side that faces the sun's direction of travel. They have told us almost nothing about the downwind side. The shape of the tail, if there is one, remains unmeasured. The map of the heliosphere remains a map of one side only. The stars that the sun is approaching in the direction of Hercules have their own stories, their own planetary systems, their own long histories of formation and evolution. None of them will be reached in any human-relevant time frame. The distances are too vast, and the speeds involved, though enormous by any earthly standard, are still tiny compared to the scales of interstellar space. The sun is approaching the Hercules region of the sky at 20 kilometers per second, but the nearest stars in that general direction are still many light years away, and the sun will require tens of thousands of years to close even a fraction of the distance. The star Vega, one of the brightest stars in the northern sky, sits relatively close to the direction of the solar apex. Vega is approximately 25 light-years away from the sun. It is a much younger and more massive star than the sun, burning hotter and bluer. It has a large disk of dusty debris surrounding it, the remnant of its own planetary formation process, or the ongoing product of collisions among small bodies in its outer system. Whether Vega has planets is still being studied, but the disk suggests it has at least the raw material from which planets could have formed or be forming. Vega is not in the direct path of the sun's travel. The solar apex sits near Vega's position in the sky, but not precisely on it. The sun is heading in Vega's general direction the way a ship heading north is heading in the general direction of any northerly city without necessarily heading toward that specific one. In roughly 450,000 years, Vega will make its closest approach to the sun, passing at a distance of roughly 14 light-years before the two stars' independent motions carry them apart again. It is not a close approach by any meaningful standard. 14 light-years is 4 times the distance of the current nearest neighbor, but it is a reminder that the stellar neighborhood is not static. The stars move. Their distances from the sun change over time. The night sky, as seen from Earth, looks different to observers 100,000 years in the past than it does today, and it will look different again 100,000 years in the future. Let the picture expand for a moment from the immediate to the deep. The sun has been traveling through the Milky Way for 4.5 billion years. In that time, it has completed roughly 20 full orbits of the galactic center. Each orbit has taken it through different regions of the galaxy, through different interstellar environments, through the denser regions of spiral arms and the quieter regions between them. The history of those passages is encoded, imperfectly but legibly, in various records. In the composition of ancient meteorites, in the abundance patterns of certain elements in the solar system compared to the broader galaxy, in the long geological and biological record preserved in the rocks and fossils of the Earth. The composition of the Sun and the solar system reflects not only the conditions in the local region of the galaxy at the time of the solar system's formation, but also the history of stellar generations that came before. Every atom of carbon in every living thing on Earth was forged inside a star that lived and died before the solar system existed. The iron at the Earth's core, the oxygen in the atmosphere, the calcium in bones, all of it was produced by nuclear reactions inside stars that completed their lives before the sun was born and scattered their material back into the interstellar medium from which the solar nebula eventually condensed. The sun's motion through the galaxy has carried it through regions enriched by the deaths of different generations of stars. The composition of the interstellar medium varies across the galaxy, with older regions in the galactic center tending to be richer in heavy elements produced by many generations of stellar evolution, and younger regions toward the outer galaxy being somewhat less enriched. The sun's orbit has kept it in the middle regions of the galaxy for its entire history, sampling a moderately enriched environment throughout its life. The chemistry of the solar system, and through it, the chemistry of every living thing on Earth, reflects the particular galactic neighborhood through which the sun has been traveling for 4.5 billion years. The motion toward the solar apex has been continuous for the entire history of the solar system and will continue for the entire remaining future of it. The Sun is not accelerating toward Hercules in any dramatic way. It is not on a collision course with anything visible. It is simply drifting steadily forward on its long galactic circuit, carrying its family of planets along, encountering the slow variations of the interstellar medium as they come, adjusting the heliosphere to match the external conditions, and leaving behind in its wake the long history of environments through which it has passed. The future path of the Sun through the galaxy can be traced approximately for hundreds of millions of years using the known properties of the galactic gravitational field and the Sun's current position and velocity. The trace is approximate because small uncertainties in the current position and velocity accumulate over long timescales, and the galactic gravitational field has its own complexities, from the spiral arms, from dark matter, from the massive black hole at the galactic center, from the distributed mass of the disk and the halo. But the broad outlines of the Sun's future trajectory are known well enough to describe. In roughly 10 to 20 million years, the Sun will enter the next spiral arm it encounters on its galactic circuit. The Sagittarius arm lies inward from the Sun's current position, and the Sun's orbit will eventually carry it closer to that arm before the circuit continues outward again. The passage through or near the arm will bring the Sun into a region of higher stellar density and more active star formation. The supernova rate in the neighborhood will increase somewhat. The interstellar environment will become richer and more variable. None of these changes will be sudden or violent from the perspective of the solar system as a whole. They will unfold over millions of years, too slow to be called events in any ordinary sense, and their effects on the Earth and its inhabitants, whatever inhabitants there may be at that future time, would be long-term statistical influences rather than catastrophic episodes. Beyond that passage, the circuit continues. More interarm quiet, more arm crossings, more passages through different interstellar clouds and cavities. The vertical oscillation above and below the galactic plane continuing alongside the horizontal circuit, the heliosphere breathing in and out in response to the changing external pressure, the long patient repetition of the galactic year, carrying the solar system forward through a galaxy so large that 20 circuits in 4.5 billion years barely begins to explore it. There is something worth sitting with in the sheer steadiness of the motion. The Sun has been heading toward the direction of Hercules, or at least toward whatever direction corresponds to the current solar apex, for longer than the Earth has had oceans. The motion has not paused. It has not wavered significantly. It has not reversed. It is one of the most persistent facts about the solar system, more persistent than any mountain range, more persistent than any ocean, more persistent than any feature of the Earth's surface that has ever been named or mapped. The Sun simply continues forward. The direction in the sky that marks the forward point of that motion continues to receive the approach of the solar system at a steady pace that has not changed in any way that matters for this evening's consideration. The direction behind the Sun, the antipex in Columba, contains the long record of where the system has been. Every region of the galaxy the Sun has passed through in its 20 galactic orbits lies in some sense behind that direction. Every interstellar cloud that once surrounded the heliosphere and has since been left behind. Every spiral arm that was once the Sun's immediate neighborhood and is now a distant structure far back along the orbit. The history of the solar system's cosmic travels is stored, at least in principle, in the direction of the antipex. In practice, it cannot be recovered in any direct way. The past environments have dispersed. The evidence is indirect and fragmentary, but the geometry of the motion preserves its logic. What is behind was once ahead. What is ahead will someday be behind. The solar apex is the direction of what has not yet been encountered, and the antipex is the direction of everything that has already passed. The stars visible in the direction of Hercules on a clear night are not the immediate destination of the solar system. They are simply the background against which the forward direction of motion is projected. The actual region of space that the solar system is moving into is the local patch of the Milky Way immediately ahead along the Sun's path. The stars of Hercules are mostly dozens or hundreds of light years away. The Sun's motion will carry it appreciably toward them only over timescales of millions of years. On the scale of a human life, they are as fixed and as unreachable as any other star. But there is something quietly meaningful about knowing which direction in the sky is forward. On any clear night when Hercules is visible, the small, not quite prominent constellation sitting between Lyra and Corona Borealis in the northern sky, the direction of the future, is written into it. The solar system is moving toward that part of the sky right now. As the listener rests here tonight, the entire solar system, sun and planets and moons and comets and every spacecraft ever launched, is drifting steadily toward the general region of Hercules, not quickly enough to notice, not in any way that changes the appearance of the sky over a human lifetime, but steadily, continuously, without interruption. The direction of Hercules contains no obvious landmark for the solar apex. It is not a bright star. It is not a dramatic nebula. It is a quiet region of the sky, moderately populated with ordinary stars, without anything that announces itself as the forward direction of the sun's travel. The solar apex is marked only by the mathematics of stellar motion and the careful analysis of how nearby stars drift against one another over time. It requires patience and measurement to find. It is not visible as a destination, but it is there in the direction of Hercules, receiving the approach of the solar system at a pace that has never varied for as long as the solar system has existed. The other stars of the galaxy are also moving. Every star in the Milky Way is orbiting the galactic center on its own trajectory, shaped by its own particular history of formation and gravitational interaction. The local stellar neighborhood, the several hundred stars within roughly 50 light-years of the Sun, is not a fixed community. Its members drift past one another on their individual orbits. The stellar nearest neighbors change over time. The night sky, as seen from Earth, changes on timescales of tens of thousands of years as nearby stars drift past and their parallax shifts change their apparent positions. The sun's motion through the local neighborhood at 20 kilometers per second relative to the average stellar motion means that the identities of the nearest stars change over geological timescales. The current nearest neighbor, Proxima Centauri, has not always been the nearest and will not always be the nearest. Stars have drifted into the near neighborhood and passed through and out again across the history of the solar system. At various points in the past, different stars have been the sun's nearest neighbors. At various points in the future, stars that are currently many light years away will become temporarily closer than the current neighbors. The approaches of other stars to the solar system are of interest not for any risk of collision, which is essentially zero given the vastness of interstellar space, but for their gravitational effects on the outer reaches of the solar system. A star passing at a distance of 1 or 2 light years exerts a small but measurable gravitational perturbation on the Oort cloud, the vast spherical reservoir of comets that surrounds the solar system at its outermost edge. Such perturbations can deflect cometary orbits and send some comets falling inward toward the inner solar system. The history of close stellar encounters is therefore connected through the Oort cloud to the history of cometary impacts on the Earth and the other inner planets. The long record of impacts preserved in the crater records of the Moon and the other solid bodies of the solar system carries within it a faint memory of the stellar passages that influenced the Oort cloud over
sun is a traveler. This is the quiet fact that tonight's exploration has been slowly building toward, not a stationary hub, but a traveler, carrying its planets and its wind and its bubble of protection through a galaxy that is itself rotating, itself evolving, itself drifting through the local group of galaxies in its own larger motion. The solar system is embedded in nested layers of motion, each layer carrying the next, each motion adding its component to the total velocity of everything you have ever known relative to the universe at large. The Earth moves around the Sun. The Sun moves around the galactic center. The Milky Way moves through the local group. The local group moves toward the Virgo cluster. The entire local supercluster drifts toward the Great Attractor, a massive concentration of matter hundreds of millions of light years away, whose gravity pulls the surrounding universe toward it. Every one of these motions is real. Everyone is ongoing. Everyone is adding its component to the velocity of the particular atoms that make up the listener's body relative to any sufficiently distant reference point. The solar apex is only one of these motions, but it is the most local one, the most immediately relevant one, the one that is carrying the Sun through the particular stretch of the Milky Way in which the solar system currently finds itself. The direction in Hercules toward which the Sun is heading is the most personal of the solar system's many directions of motion. It is the forward direction, the direction into which the next few tens of thousands of years of the solar system's cosmic journey are aimed. The awareness of the solar apex was a discovery that required careful observation over a long time. Herschel's deduction in the late 18th century was refined over the following 2 centuries as the number of stars with measured velocities increased and the statistical analysis became more precise. By the early 20th century, the location of the solar apex was well established. By the middle of the century, the speed of the Sun's motion relative to the galactic center had been measured. By the end of the century, the detailed structure of the local interstellar medium and the Sun's position within it were becoming clear. The picture that emerged over those 2 centuries of measurement was one of a solar system in continuous motion through a complex and variable environment, not drifting through empty space toward a fixed destination, moving through a galaxy that is itself in motion, through an interstellar medium that has its own structure and variation, past other stars that are themselves moving, through regions shaped by the deaths of ancient stars and the births of new ones, along an orbit that has carried the system through many different neighborhoods over its long history. The direction of the solar apex in Hercules is a snapshot. It is the current forward direction of a motion that has been changing slowly over the long arc of the Sun's galactic orbit. In another 100 million years, the solar apex will point in a somewhat different direction as the Sun's galactic orbit carries it around another portion of its circuit. The direction in Hercules is not permanent. It is the current heading, the direction toward which the next chapter of the solar system's journey is aimed. There is a particular quality to the knowledge that the solar system is moving and that the direction of that motion can be located in the night sky. It is not an alarming knowledge. There is nothing threatening about the solar apex. The direction in Hercules is not the direction of any hazard. The interstellar environment ahead is not significantly different from the one the Sun currently occupies. The transition from the local interstellar cloud into the broader local bubble will be gradual and gentle, unfolding over thousands of years in ways that are impossible to detect on any human timescale. The knowledge is instead a kind of quiet orientation, the feeling of knowing which way the ship is heading, not toward any dramatic destination, not with any urgent purpose, simply the awareness that there is a forward direction to the solar system's drift through the cosmos, and that this direction can be found in the night sky on any clear evening when Hercules is above the horizon. The forward direction is in Hercules, the past direction is in Columba. The sun sits between them, carrying its family of worlds steadily forward at 20 kilometers per second relative to the local stellar neighborhood, 250 kilometers per second relative to the galactic center, at whatever larger velocity applies relative to the universe at large. All of these numbers are ongoing. None of them pause. None of them require anything of the listener tonight. The shape of the night sky carries the solar system's motion encoded within it. The stars in the direction of the apex appear to be spreading slowly apart. The stars in the direction of the antipex appear to be drawing slowly together. The shift is too slow for any human eye to detect over a lifetime or a generation or a century, but it is real, continuous, and geometrically inevitable. It is the motion of the solar system written in the slow drift of the stars, visible to instruments and mathematics, if not to the naked eye. The zodiacal light, the faint cone of dust-scattered sunlight visible on clear evenings along the plane of the planets, is brighter on the upwind side of the solar system, toward the solar apex, because the motion of the sun through the interstellar medium tends to concentrate dust and small particles on the forward side of the heliosphere. The distribution of interplanetary dust is subtly asymmetric, skewed slightly toward the direction of travel. The faint glow of the zodiacal light is therefore not perfectly symmetric around the ecliptic, but slightly enhanced in the direction of forward motion. It is a small effect and not easily detectable without careful measurement, but it is there. The light of the night sky carries the motion of the solar system embedded within it at every level, from the obvious to the subtle. The two spacecraft that have crossed the heliospheric boundary both did so on the upwind side, the side facing toward the solar apex. They entered the interstellar medium through the compressed nose of the heliosphere and began sampling the local interstellar environment from that direction. Their transmissions, arriving at Earth after 17 and 20+ hours of travel time at the speed of light, carry the first direct measurements ever made of the conditions immediately beyond the heliospheric boundary in the direction the solar system is moving toward. The measurements are still arriving. The spacecraft are still functioning barely, transmitting at the lowest data rates their aging systems can manage, but still sending. The data they return is irreplaceable because no other spacecraft has ever been where they are or is currently heading there. The motion continues tonight as it has always continued. The solar system advances toward Hercules at the same pace it has maintained for billions of years. The interstellar medium parts slowly around the heliosphere's nose and closes slowly around its wake. The local interstellar cloud surrounds the heliosphere on most sides, pressing gently inward. The boundary of the heliosphere holds, maintained by the balance of pressures that has been keeping it in place across the sun's entire history. The planets circle the sun on their ancient orbits, each orbit a small thread in the great fabric of the heliosphere, each planet carried forward along with the sun toward the direction of Hercules at the same steady pace. The Earth completes its yearly orbit around the sun, and the sun carries that orbit forward through the galaxy. The moon circles the Earth, and the Earth carries that orbit around the sun, and the sun carries both forward toward Hercules. Every motion is nested within the larger motion, and all of them together constitute the long forward drift of the solar system through its corner of the Milky Way. The direction in Hercules is waiting ahead of us the way the horizon waits ahead of a ship. Not a destination in any meaningful sense, not a place that will be reached, simply the direction of the next moment and the moment after it, and all the moments that follow for as long as the sun continues to shine. The horizon of the solar system's cosmic journey points tonight toward Hercules, and it will point in approximately that direction for as far into the future as any reasonable calculation extends. Let the awareness of this settle slowly. The solar system is moving. The direction is in Hercules. The speed is enormous by any human standard and negligible by galactic standards. The interstellar medium ahead is quiet and thin and not dramatically different from what surrounds the heliosphere today. The future of the Sun's journey through the galaxy is long and gradual, and full of slow changes that will unfold on timescales that make even geology seem hasty. None of this needs to be held tightly. The awareness of the solar apex is the kind of knowledge that rests more easily when it is not gripped. It is not useful information in any practical sense. It does not change anything about tomorrow. It does not resolve any question that requires resolution before sleep. It is simply the shape of where the solar system is going, offered quietly at the end of an evening, as a kind of gentle orientation in the larger space that contains everything.
The Sun continues its long circuit. The planets continue their shorter ones. The forward direction continues to receive the approach of the solar system at its steady pace. The stars of Hercules continue to drift imperceptibly apart as the Sun approaches them. Columba sits in the southern sky, holding the direction of everything the solar system has already passed through and left behind. The motion does not pause for the night. It does not require attention or acknowledgement. The solar system advances toward its current forward direction, whether anyone is watching or not, whether anyone is awake or not, whether the knowledge of the apex is present in anyone's mind or has been allowed to quietly dissolve into sleep. Let your breathing slow. Let the direction of Hercules rest in the sky where it has always been. Let the long forward motion of the solar system continue as it always has and always will. Let the enormous steadiness of it settle around you like the night itself. The Sun is moving, everything is moving, and all of it is quiet, and all of it is slow, and none of it asks anything of you tonight. The direction of the future is in Hercules. The direction of the past is in Columba, and right now, in between the two, the solar system drifts steadily forward, carrying you along as it has carried everything you have ever known through the long, patient,